Hi, welcome everyone. The session 10 of mentoring for a career in machine learning. So, today in the first session, we will look at one of the most important topic in machine learning that will be utilizing or leveraging whenever we build machine learning models. It's called k-fold cross validation. Also, we will look at hyperparameter tuning, how to find the optimal values for the hyperparameters, and what techniques we have, and how do we actually use cross validation while tuning the hyperparameters. For today's session, as well, I have created a folder called session 10 in the GitHub location, and there is a file called k-fold cross validation underscore v1, and let's open that. So let's open the k-fold cross validation v1, and the topics that we are going to discuss in this particular session, in this particular notebook. The first is the limitations of using only one train and test split, and how do you overcome that with a k-fold cross validation. So what is k-fold cross validation, and how it helps to better estimate the model's performance? That's what you're going to understand today. And then of course the hyperparameter tuning. For this also we will use the same data set, the data set that we use for predicting the resale price of a used car. So let's go ahead and load the data set. And let's look at few samples. We will go through the initial steps quickly because we have already gone through the steps many times. As usual, the data contains, the sample set contains about 1,000 samples. And for this particular example, we'll be taking only 6 features: the fuel type, transmission, owner type, age, model, and kilometer driven. And besides age and kilometer driven, the rest all are categorical variables. So let's create a list of X features, and these 4 are the categorical: fuel type, transmission, owner type, and model, and the remaining are numerical features. So we'll create the X and Y variable. The X will be the subset of the features from the cost TF mentioned in the X features, and the Y variable will be the price. Again, we'll split the data set into 80 and 20 ratio. So we have 800 samples in train and 202 samples in test. And creating pipelines for feature transformation. As you know, we will be using one-hot encoding for the categorical features, and for numerical features, we'll be actually using min-max scaling. And we have imported all required classes, initialized one-hot encoding, and created a pipeline for one-hot encoding. Similarly, we have instantiated min-max scaler and created a pipeline for scaling. And here in the column transformer, we have mapped the numerical transformer to the numerical variables, in this case age and km driven, and the categorical transformer for remaining all categorical features, the 4 features. And then we'll be building a KNN model like last time. In the session 9, we have already done this. So let's initialize the KNN neighbors regressor. We are using a regressor in KNN because this is a regression problem. As I told you, the KNN can also be used for classification, but we will explore that when we come to a classification problem later. And in this case, we'll be using 5 neighbors. We have hard coded this here, and the weights is uniform. That means the price, the resale price of a new car would be estimated from the 5 neighbors by taking the simple average of the prices, resale prices of these 5 neighbors. So it has two options as we discussed last time. One is of course uniform, we have utilized here. The other one is distance. Right? So the nearer neighbor will have higher influence on the estimation of the price compared to the neighbors which are further away. So in this case, I have hard coded both of them, but later we will find out how to find the optimal values for these two using hyperparameter tuning. So these two are hyperparameters. So let's create the final pipeline which contains the preprocessor, which will transform the categorical and numerical features, and then the model canon. And we will train the model now. As you have already seen this before, the numerical features gets transformed to min max scaling. The categorical features gets transformed to the one-hot encoding, and then we feed the transform data to the k neighbors regression here. And then when we predict that on the test data, and we measure the R2 score, it comes out to be 0.855. So this is what we had done in the last session until this point. Now today's topic is, now is this 0.855 that we are achieved by predicting on the test data, so is this the actual accuracy of the model? Or is it because of the chance by which we created a train and test set in a particular split, we are getting this accuracy? What would happen? Now what happens if the training set and test set changes? So now what if a different samples go into train and different samples go into test, and if we train the model on the new training set and we test it on the new test set, so is my accuracy going to be remain same, or is it going to change? Or if it changes, how much it should change? If it's a drastic change, what does that actually indicate about the model's performance? So we need to investigate all that. So how do we now change the train and test set? One of the easier way is to basically change the random state. So when we split the data set here, we gave a random state, so which ensured that certain instances of the data set goes to the train and certain instances go to the test set. Now if I change the random state here, let's say I change to 40 or 20 or 100, so every time I change this, out of this 1010 samples, the samples that go to train and go to test, they would differ. So in a way, we can bootstrap different train and test sets by simply changing the random state here. So let's do that once and see what happens. So let's say I'm going to change this random state to 200 now. So we'll ensure that my train set and test set completely changes. So of course, some of the samples that already were there in the train will remain, but new samples would come, and some of the samples on the train would go to test. So it will look like as if there's different train and test sample, isn't it? Now, once we split that, let's build the pipeline again with the new train and test and measure the accuracy. Now the accuracy seems to be 0.87. What we achieved earlier was 0.85, now it says 0.87. Then what is the actual accuracy of the model? Is it 0.85 or is it 0.87? Because moment you change a train and test set, the accuracy seems to change, which is expected, of course. Now, if we had used only one train test split, we would have assumed that the accuracy is 0.85, now it is changing. So the limitations of using only one train and test split is relying on a single train test split of measuring model's accuracy can lead to bias, variability, and lack of confidence in the reported performance. Right? So we don't know how much it will vary. Typically, we measure a confidence interval, which we have already discussed in the one of the previous sessions, of the model's performance. That means rather than giving a point estimate saying that the model's performance is 0.85, we can actually estimate the model's performance remains or lies between what point to what point, right? So we can actually measure that only by taking multiple different train and test splits. So if you use only one train and test split, the performance of the model can be highly dependent on specific instances, right? And if the split happens to be unrepresentative of the overall data distribution, the obtained accuracy may not reflect the true performance of the model. So in some cases, what might happen is if we take a train data and a test data, from the complete data set, this is the complete data set. Now when we build a model out of the train data, and if you change few samples here in the train data, right, and if you change few samples in the test data, for example, some of the test samples we bring it to train now, and some of the train samples we take it to test data, right? So it will change the representation of the samples in the train and test data, and we will rebuild the model again. Now we need to observe how the accuracy changes. If the accuracy changes significantly, what does it actually mean? And typical expectation is even if we change the samples, right, the model's accuracy should not change drastically, right? It will change, of course, because there will be variations. So, but it should not change much, which should also indicate a kind of the robustness of the model. So that's what we need to observe. If the model changes significantly, that means it's picking up the local patterns in the training data and not able to generalize well. So one way, of course, is to kind of create multiple different train and test sets and measure that, or there are multiple techniques, and one of the most widely used technique is called k-fold cross-validation technique. So in the k-fold cross-validation technique, what we do is we take the whole data and first split into two sets. One is called train data and test data. Now this test data typically is not utilized during the process of model development. This is only utilized only for the final testing of the model. When I say final test, once we have selected the best model during the model development process. So let's first understand how the k-fold cross-validation works, and then we will go and look at how this is leveraged in the model selection process. Now take the train data and split that train data into multiple folds. Now imagine if you have a 800 samples here and 200 samples here, and that total 1000 samples in the complete data set. And out of 800 samples, what we do is we create, let's say, 5 folds here. Typically the k value indicates how many folds we want to create, and the typical value we use is k equal to 5 or 10. If it's a very large data set, several thousands, probably you can use 10, or you can just use 5 folds. So here what will happen is Now each fold will contain about 160 samples here, randomly, not in any sequence. So 160 samples. So we call it a fold 1 or K1 or K2, K3, K4 and K5, right? So fold 2, fold 3 and all that. So in what we do is, first when we build a model, let's say we build a model called KNN with a number of neighbors is equal to 5 and the weights is equal to uniform. So this is the model that we want to build, and we want to understand the performance of this model. Then what we do is, we out of this 5 folds, we take 4 folds, right, as our training set, and leave out one set as a test set. So you build the model on the 4 folds here, let's say 2 to 5, and test it on the first fold, and then we measure the accuracy, R square. Let's call it R square 1. And then again we build the model with fold 2 as my test set and the remaining ones as my training set. Let's call it a R2 square. So every time we take a different fold as my test set and the remaining ones as my train set. So in a way, my train set and test set keeps changing, right? And we keep measuring the R square value. So we'll have now, we'll repeat the whole process of building or training and testing models here 5 times, because the K is 5. So this can be repeated 5 times, and every time we get a different accuracy here. And then we look at this accuracy and we kind of get an insight how good the model is. And for that we can actually measure 2 things. One is, what's the average of all accuracy, right? What's the average of all accuracies? So R square value, what's the average of all accuracy, and how much it is varying. You can also calculate the standard deviation of all the R squares. So the mean estimate of R squares gives a better estimate of how the model's performance is, and the standard deviation of this R squares gives you how much the accuracy varies. If the variance is, or standard deviation is very high, then we know that the model is not very reliable, and it's the whole process of learning and prediction is very uncertain. If the variance and standard deviation is very low, then we know that the model is quite robust and very reliable. And then we can use the test data for the final validation, but we don't use it for all models. So typically what we do is, in the process of model development, so let's look at one example right here. So this is the complete data set, and then we create a train set out of this, and test set, right? And this test set is not leveraged or utilized until the final model is formed. And this train set is now split into 5 folds. So K1, K2, K3, K4 and K5. Now let's say we are now experimenting with multiple different models. In this case, let's say we're trying to find out which KNN model is the best. So whether a KNN model with a neighbor of 5, I'm just going to keep it to only one hyperparameter for explaining. Whether KNN model 10 with the 10 neighbors is better, or KNN model with 20 neighbors is better. Now, to understand the performance of the model KNN with only 5 neighbors, so we'll repeat the model training and test 5 times here. So we will first take, let's say, K1, K2, K3 and K4 as my train data, and K5 as my test data. Then I will take K1, K2, K3 and K5 as my train data and K4 as my test data. And then I'll keep measuring my R square values here. And this process I'll repeat how many times? 5 times. For only KNN with 5 neighbors. And then I'll measure the average of R square value and the standard deviation of R squares. Then I repeat the whole same process for KNN with neighbor 10, again 5 times, right? Again, I will measure the R square value, average of R squares, and the standard deviation of R squares. Same thing for KNN 20. So you can see, so this is one model experiment, this is another model experiment, and this is the third model experiment. So I am going to repeat this process for as many experiments as I want to do, and then I will measure the average R square value and the standard deviation of each of the models. Then I can compare them. Typically what we do is we look at the standard deviations. The standard deviation is very high. This is of course very subjective in an experiment. Very high. Then we eliminate the model, saying that the model is not very reliable. And among the models where the standard deviation is very low, typically we can say less than 2%, 1 or 2%, right? And among them we look at which model has a higher R square value, the average value. So that model we select. So in this case, let's say the model KNN10 gives the best average R square value with a very low standard deviation. The model is reliable, and also model's average performance is quite better compared to other models. Then we take this KNN model 10. Now we can train the model on the complete train data and then test it against the test data. So the test data is kept to test the performance of the model, which is the best that we have found during the model development process. We don't overutilize this in the process of every model experiment. There's a possibility that some of the information from the test data might leak into the model development process. So we'll keep it aside, right? And we test the model's performance at the end once we have found the best model during our model selection process. And that accuracy that we get out of the test data now, R square which we get of the test data, which can be used as a benchmark how the model would behave or perform in the production when you deploy the model in the real world. So this is the typical step that we follow when you do a model selection and models validation process. Now going back to the notebook, now it provides more comprehensive evaluation of the model's performance across different data subsets. We also better utilize the data because it allows us to make efficient use of the available data. In traditional train test split, when we use only one train test split, a portion of the data is used only once for testing, which reduces the amount of data available for training. With the k-fold validation, every data point is used both in training and validation, leading to a more reliable estimation of performance. Now, how do we do that? The scikit-learn provides a technique, a method called cross-val score. So you can import that, which is a part of model selection. And then we call cross-val score and pass on the pipeline, KNN pipeline that we have built. And then give X-train and Y-train, the training sets. And here we provide the K value. The K value is 5. So here the parameter they are calling it CV, which stands for cross validation, which is same as K. Okay, K-fold cross validation. Please remember, there are typically the K value is used with as a parameter. So the K in the KNN is different than the K in the K-fold. Okay, so K in K-fold is number of folds that we want to create. The K in KN is the number of neighbors we want to use. So in this case, of course, we have hard coded the K for KNN as 5. and then the scoring. So we give the model, the pipeline, the complete train data, X and Y, the K value, how many folds it would create on this train data, and then what performance would be measured. Here in this case, R square, because we given R2, because this is a regression model. So this particular method can be leveraged across many different kinds of models. So you can use it for regression, we can use for binomial classification, multinomial classification. Based on that, we have to give the appropriate scoring. Because we are using a regressor here, and our objective is to find the R square value. Now when you run this, it returns the R square value of all the 5 folds, right? All the 5 repetitions of the train and test set. So now if you look at the scores, you see the scores now look at one is 0.85, 8539, 0.82, 0.85, and 0.85. You can see that it typically stays very consistent. There isn't much variations in the model's performance, which it indicates that the model is highly reliable. And what is the better estimate of the model accuracy? We can look at the mean value for all the scores. So that's a more reliable one, 0.85. And if you look at the standard deviation, it's a very low, 0.01, which is very good. So this itself gives you some indication into the model's performance, the fluctuation in that, the variability in the model's performance, which would indicate the reliability of the robustness of the model. So how do we interpret the cross-validation scores? Mean accuracy. Mean accuracy represents the average performance of the model. If the mean accuracy is high and consistent across the folds, for example, in this case, it's quite consistent, 0.85, 0.85, 0.85. It indicates the model is performing well and likely to generalize to new data, right? Well, variance. Look at the variance and standard deviation of the accuracy value across the folds. A high variance, that means high variability in the model's performance across folds, suggests that model's performance is sensitive to the specific data splits. It indicates instability or inconsistency in the model's prediction, right, when faced with the different subsets of the data. Okay. Typically, high variance is a no for the model selection. It also indicates some amount of data quality and quantity. Variance in the model's accuracy could also be influenced by the quality and quantity of the available data. So which also indicates the data quality may not be good, or the quantity is just not sufficient. If the data set is small and contains high level of noise and outliers, it contributes to increased variance. So increase the amount of data and improving quality can potentially reduce the variance. So this is one step that you can take. If the standard deviation is very high, you can probably check that model data quality may not be good. And this process can also be used for model selection and hyperparameter tuning, which will be, of course, the topic of the next. Hyperparameter tuning using grid sets. So what you can do is we can utilize this method now to do the to find the optimal parameter. Like I decided, we can actually build a model with KNN with the number of neighbors is 5, or number neighbors is 10, 15, and 20, and each one we will do 5 times cross validation, right? 5 times k-fold cross validation, and then measure the average accuracy score, and then we'll observe which hyperparameter gives the best accuracy. That's basically called your hyperparameter tuning. Okay. So in grid search, we define a grid of hyperparameter values to explore. So all possible combinations. For example, let's say we want to search with both the hyperparameters, number of neighbors and the weights. So what you can do is you can create a grid. For example, let's say the number of neighbors is 5, right? And the weights is uniform, right? The number of neighbors again 5, the weights is distance. The number of neighbors is 10, now uniform. Number of neighbors is 10, again distance, right? And then what you can do is the grid search algorithm exhaustively searches through all possible combinations of hyperparameters to find the optimal set of fields. So the grid search is basically a brute force approach. It experiments with all possible combinations and gives the best performance metrics such as R square value in this case. The performance of each combination is compared and hyperparameter set with the best performance is selected as the optimal choice. So what I do is now, to do this, we have a method called grid search, class called grid search CV in scikit-learn. Let's import that, model selection grid search CV. And then first we'll define the pipeline, which is a k neighbors regressor. But one difference that you see here when we define this pipeline, we are not providing any hyperparameters here. We are not providing hyperparameters. We are calling the default constructor here without passing any parameter, right? And then of course we're creating the final pipeline for pre-processing and KNN. And now these parameters would be specified as a grid. So it's called param grid. We're saying that now it's given as a dictionary here, saying that for the KNN model here that we have specified in the pipeline, KNN, so we have to specify that as a prefix to it. And then in that model, there is a parameter called n neighbors. This has to be based on the model that we are going to use, because we are using k neighbors regressor here. We are using its parameter n neighbors, which should be varied from 5 to 30 with a step of 2. So we will actually experiment with what happens if the number of neighbors is 5, then 7, then 9, then 11. This of course we can change. I have limited to only very few specific values, 13 and so on and so forth. Similarly, the weights parameter also should be varied between uniform and distance. They are specific values. So 5 uniform, 7 uniform, 9 uniform, and so on and so forth. Again, 5 distance, 10 distance, and so on and so forth, right? So all possible combinations, right, are provided in the param grid. So this KNN model, that's a default construct that we're given, would be initialized with each combination and then it'll be cross-validated. So once we initialize this, so this is the search space, right? This is the search space that we provide. So among what possible combinations it should find what's the optimal value. So now the grid search CV, we provide the KNN pipeline here. Then we provide this grid here. So what are the possible values that can be utilized? And how many cross validations? So each combination, like 5 with the uniform, it will be cross validated 5 times and the score R2 would be reported. So this grid search CV, once we initialize this and we fit the model, and it'll take a little while because it's doing many different model buildings. Now of course it's done here. Now if you look at how many models are created here, let's say 5 to 30 with a step of 2. So it's a, let's say about the difference is 25 divided by 2. Let's say about 12 different possible values for the n neighbors, and 2 possible values for the weights. So 24 possible combinations, right? And each combination is now validated 5 times. So 24 into 5, that will come out to be 120, right? Model training process that happens underneath. to find the best possible parameter values. Now, once you fit the model to the grid search CV, to the train and test data, it would have automatically figured out what is the best parameter. Now you can ask what are the optimal values of the parameters. So if you say best param, it's saying the best parameter is if you use 7 as the number of neighbors and distance as the weights. So that is giving the best score. And what is the best score? The 0.8531. That's an average of all cross validations, average score, right? So that's a best parameter. So the KNN grid that we have defined here has two parameters, best params and best score. We can also little deep dive detail into the results. So you can look at the metrics that it has obtained through all possible combinations. The KNN grid has a has a variable called CV underscore results. So you can wrap that in data frame and look at that. So this is an interesting information. And we can see it provides a lot of information. We'll probably go through one or two. For example, one combination is 5. One combination is 5 and uniform. You can see 5 distance. It has tried all possible combinations, 7 uniform, 7 distance, 9 uniform and all that, until if you scroll down until it's 29, because up to 30, 29 uniform and 29 distance. So there are 25 total, 26 combinations in fact, not 24, 26 combinations. And each combination, it tells that it goes to the 5 cross validations. So 5 cross validations, 1, 2, 3, 4, 5, the 5 different validations. So this is the cross validation R1 square, R2 square for 5 and uniform, and that's the average of this 0.85, and that's a standard deviation of it. And if you look at the now mean value of the test scores for all the possible combinations, this seems to be the best. That's what we got, right? Which is nothing but our 7 and distance. This gives the best score. And it also provides a column called rank, which gives automatically which is the best. This is the best, this is the second best, this is the third best, and so on and so forth, right? Typically we don't directly take the ranks from this particular results, because this is purely based on which is the highest mean square. We normally look at the standard deviation and eliminate if any of these have a very high standard deviation. Okay, typically you have to observe that. And we know, but here in this case, of course, none of them has a very high, except probably this is a little higher, this one, 0.2, 0.2. The rest all are more less than 0.1, right? So we can actually rely on this particular ranks here. So finally, because we've now found the best hyperparameter, which is 7 and distance, okay, then what you can do is you can finally build the model. So you can initialize neighbors with the 7 and distance and create the pipeline and fit to the train data now, the complete train data now, and test it against the test data, which comes out to be now 0.86. So this is probably the benchmark for this particular model. Once you've chosen the best model among the possible combinations. So this is an important topic. So in this topic, in this notebook, we learned 3 things. One is what are the limitations of using only one train and test set. Then k-fold cross validation to overcome that particular limitation. And in the k-fold cross validation, we obtain the mean model performance or the standard deviation of the model's performance score, and how to interpret that, right? How to take that and understand models performance and choose models. And then we also understood how to do hyperparameter tuning, right, using the grid search technique. So these are the key topics that we learned in the notebook. In the next session, the second part of this session 10, we will look at some more advanced topics of the KNN. So see you then.